Welcome to today's explainer. If you've been anywhere near the news, the stock market, or literally just the internet lately, you know Nvidia is everywhere. They've got this massive, almost gravitational pull right now. But how they actually built this tech empire, that is an absolute masterclass in strategic evolution. So today, we're on a journey to figure out exactly how they pulled it off by looking under the hood at the chip architecture that drove their incredible ascent. And that brings us to the ultimate question we'll be unraveling today. How in the world did a piece of hardware, originally just meant to make 90s PC video games look a little bit better, turn into the undisputed engine of modern computing and artificial intelligence? To get there, we really need to look at the numbers. Just wrap your head around this staggering number, 80%. That is Nvidia's estimated chunk of the entire global AI chip market right now. They aren't just riding the AI wave, folks. They are quite literally providing the infrastructure for it. But, this kind of sheer dominance absolutely didn't happen overnight. It was built on a series of incredibly calculated risks and very specific architectural choices. So let's rewind a bit to April 1993. Believe it or not, this trillion-dollar giant was actually founded at a Denny's diner in San Jose. Over a few Grand Slam breakfasts, founders Jensen Huang, Chris Melikovsky, and Curtis Preem dreamed up a way to completely revolutionize graphics processing. But, well, it wasn't exactly smooth sailing at first. In 1995, their very first chip, the NV1, basically flopped. It was optimized for these four-sided quadrilateral shapes, which completely clashed with Microsoft's triangle-based industry standard. But hey, they learned their lesson fast. By 1997, they pivoted to triangles with the Riva 128, scored their first massive commercial hit, and honestly set the stage for something legendary. Fast forward to 1999. Nvidia goes public, but the real game changer happens on October 11th. They dropped the GeForce 256. And they didn't just release a new product here. They essentially birthed an entirely new category of computing. Actually, they officially coined the term graphics processing unit, or GPU, specifically to market this exact chip. Okay, so what made the GeForce 256 so absolutely crucial? Before this came along, your standard CPU had to do all the heavy lifting for 3D graphics, a really clunky process called software transform and lighting. The GeForce 256 changed everything by introducing hardware transform and lighting. It ripped those complex geometry calculations right off the CPU and handled them directly. We're talking processing over 10 million polygons every single second. By taking that workload off the CPU, Nvidia was basically foreshadowing the exact parallel processing philosophy that would make them the undisputed kings of AI decades later. To really picture the difference here, think of your traditional CPU like a small room full of highly intelligent, but maybe easily stressed executives. They're latency-oriented. They're built to do one highly complex task at a time, incredibly fast in a sequence. A GPU, on the other hand, it's like an absolute army of simple, dedicated workers. It is explicitly parallel and all about throughput. It thrives when there's inherent data-level parallelism. Basically, when you need to do the exact same simple math operation to thousands or millions of pieces of data all at once, like, say, rendering millions of individual pixels on a screen. By the early 2000s, the raw horsepower of these GPUs was just blowing traditional CPUs out of the water. Scientists and researchers started looking at this and thought, hey, can we use this for things other than graphics? And boom, that birthed the concept of GPGPU, General Purpose Computing on Graphics Processing Units. Nvidia saw this brewing and made an absolutely brilliant move. In 2006, they launched CUDA. It's a programming model that let developers use familiar languages like C to write code directly for the GPU. Suddenly, this insane parallel computing power was unlocked for the entire broader scientific community. So let's break down how this works in practice. The whole thing relies on an offload model of execution. The main application is still running on your regular old host CPU connected to the GPU over a PCI Express bus. But the moment it hits a massive, explicitly parallel computation task, it grabs that specific workload, bundles it up with the necessary data, and offloads it over to the GPU device. That's where that army of simple workers takes over and crushes the math. Zooming in on the GPU itself, things get really wild. Inside these processing units, you'll find what Nvidia calls streaming multiprocessors, or SMX, and beating right at the heart of every SMX are the CUDA cores. These are the tiny functional units doing the grunt work, like floating-point math. A modern GPU doesn't just have a few of these, it has literally thousands of CUDA cores firing off simultaneously. It is just a breathtaking scale of concurrent processing. But here's the catch. Having thousands of cores is totally useless if you can't feed them data fast enough, right? That is where the memory hierarchy comes in. First, you've got gigabytes of main SD-RAM, plenty of capacity, but relatively slow. Step up, and you have the hardware-managed L2 cache, which is shared across all the SMX units. Get even closer to the action, and you'll find a super fast 64 kilobyte shared memory and decache block for each SMX. And finally, the holy grail, the registers. These are wired directly into the CUDA cores. Grabbing data from a register can be 100 to 1,000 times faster than digging into main memory. It's literally the difference between pulling a wrench right off your tool belt versus driving 10 miles to the hardware store. Managing how close your data is to those cores, that is the absolute key to massive performance speedups. Now, to actually wrangle all this hardware, CUDA uses a really specific software structure known as the thread hierarchy. It works like this. A program is made up of a sequence of instructions called a kernel. This kernel gets executed by thousands, sometimes millions, of individual threads. These threads are bundled into thread blocks, and those blocks are further organized into grids. This whole setup is called single instruction, multiple thread, and it is the secret sauce. It lets all those millions of threads execute the exact same sequence of instructions on completely different pieces of data at the exact same moment. By late 2012, this entire architectural philosophy peaked with hardware like the legendary GTX Titan. I mean, just look at these numbers. We're talking 2,688 CUDA cores, pumping out over 4,700 gigaflops of single precision performance and pushing memory bandwidth past 288 gigabytes per second. It was this exact kind of hardware that finally and completely bridged the gap between gaming graphics and high-performance scientific computing. Nvidia had built the perfect engine. Now, they just needed the right fuel. Enter the AI awakening. Eventually, researchers stumbled onto a fundamental truth that changed literally everything. They realized that the immense data-level parallelism you need to train an artificial neural network, basically running the exact same math over and over across mountains of data, was a completely flawless match for a GPU's architecture. Think about it. The very chips that were designed to calculate the physics of a bouncing virtual ball or render explosions in a video game, they were uniquely equipped to simulate the neurons of an artificial brain. The real watershed moment hit in 2012. A deep learning system called AlexNet achieved a stunning, completely dominant victory in a major image recognition competition. And how did it win? By tapping into the parallel processing power of GPUs. This proved beyond a shadow of a doubt that deep learning practically demands immense data-level parallelism. Recognizing this, Nvidia executed a massive corporate pivot. They shifted their primary focus away from just rendering pixels for gamers and went all in on providing the computational infrastructure to train modern AI. Now, of course, when you experience explosive growth like that, you're going to attract some pretty intense scrutiny. In September of 2020, Nvidia made a huge splash, announcing a massive definitive agreement to acquire the British semiconductor and software design company ARM Limited from the SoftBank Group for $40 billion. But, as you can imagine, a consolidation of that sheer scale immediately triggered significant regulatory roadblocks all over the globe. Despite good faith efforts from the companies to make it work, those regulatory hurdles ultimately prevented the transaction. By February 2022, Nvidia and SoftBank officially announced the termination of the deal. But what's really notable here is how forward-looking Nvidia's response was. CEO Jensen Huang simply stated, "ARM has a bright future and will continue to support them as a proud licensee for decades to come." They just absorbed the termination, kept their 20-year ARM license, and steered their focus entirely back to their core roadmap. No drama, just back to work. So where does that redirected laser focus leave them today? Well, the pace of innovation is just staggering. In 2024, they unveiled the Blackwell architecture, which boasts AI inference speeds up to 30 times faster than their previous H100 chips. And they aren't even slowing down. They've already announced their next-generation Rubin AI chips for 2026. Plus, they are expanding way beyond just silicon. Through their Omniverse platform, they're enabling industrial digital twins to simulate real-world physics. Their ultimate vision right now is completely transforming traditional data centers into what they're calling AI compute factories. Which brings us to the end of today's explainer. We've traced the incredible journey of a company that started over a plate of Denny's pancakes, building chips for 90s video games, all the way to becoming the absolute bedrock of the AI era. All by harnessing the concept of explicitly parallel processing. It really is a testament to what happens when you align the right architectural design with the perfect technological moment. So I want to leave you with this thought. As traditional data centers evolve into dedicated AI compute factories run by millions of simple workers,
What industry will parallel processing transform next? Thank you so much for joining us, and stay focused on the future.